Euclidean minimum spanning tree. A Euclidean minimum spanning tree of a finite set of points in the Euclidean plane or higher dimensional Euclidean space connects the points by a system of line segments with points as endpoints, minimizing the total length of the segments. In it, any two points can reach each other along a path through the line segments. It can be found as the minimum spanning tree of a complete graph with the points as vertices and the Euclidean distances between points as edge weights. The edges of the minimum spanning tree meet at angles of at least 60 degrees, at most 6 to a vertex. In higher dimensions, the number of edges per vertex is bounded by the kissing number of tangent unit spheres. The total length of the edges for points in a unit square is at most proportional to the square root of the number of points. Each edge lies in an empty region of the plane, and these regions can be used to prove that the Euclidean minimum spanning tree is a subgraph of other geometric graphs, including the relative neighborhood graph and Delaunay triangulation. By constructing the Delaunay triangulation and then applying a graph minimum spanning tree algorithm, the minimum spanning tree of any given plane of points may be found in time nlog n, as expressed in Baker notation. This is optimal in some models of computation, although faster randomized algorithms exist for points with integer coordinates. For points in higher dimensions, finding an optimal algorithm remains an open problem. Definition and related problems. A Euclidean minimum spanning tree for a set of endpoints in the Euclidean plane or Euclidean space is a system of line segments, having only the given points as their endpoints, whose union includes all of the points in a connected set and which has the minimum possible total length of any such system. Such a network cannot contain a polygonal ring of segments. If one existed, the network could be shortened by removing an edge of the polygon. Therefore, the minimum length network forms a tree. This observation leads to the equivalent definition that a Euclidean minimum spanning tree is a tree of line segments between pairs of the given points of minimum total length. The same tree may also be described as a minimum spanning tree of a weighted complete graph, having the given points as its vertices and the distances between points as edge weight. The same points may have more than one minimum spanning tree. For instance, for the vertices of a regular polygon, removing any edge of the polygon produces a minimum spanning tree. Publications on the Euclidean minimum spanning tree commonly abbreviated as EMST. They may also be called geometric minimum spanning trees, but the term may be used more generally for geometric spaces with non-Euclidean distances, such as spaces. When the context of Euclidean point sets is clear, they may be called simply minimum spanning trees. Several other standard geometric networks are closely related to the Euclidean minimum spanning tree. The Steiner tree problem again seeks a system of line segments connecting all given points, but without requiring the segments to start and end only at given points. In this problem, additional points may be added as segment endpoints, allowing the Steiner tree to be shorter than the minimum spanning tree. In the Euclidean traveling salesperson and path problem, the connecting line segments must start and end at the given points, like the spanning tree and unlike the Steiner tree. Additionally, each point can touch at most two line segments, so the result forms a polygonal chain. Because of this restriction, the optimal path may be longer than the Euclidean minimum spanning tree, but is at most twice as longitude. Geometric spanners are low-weight networks that, like the minimum spanning tree, connect all of the points. Unlike the minimum spanning tree, all of these connecting paths are required to be short, having length proportional to the distance between the points they connect. To achieve this property, these networks generally have cycles and so are not trees. Angles and vertex degrees. Whenever two edges of a Euclidean minimum spanning tree meet a vertex, they must form an angle of 60 degrees or more, with equality only when they form two sides of an equilateral triangle. This is because, for two edges forming any sharper angle, one of the two edges could be replaced by the third, shorter edge of the triangle they form, forming a tree with smaller total length. In comparison, the Steiner tree problem has a stronger angle band. An optimal Steiner tree has all angles at least 120 degrees. The same 60 degrees angle band also occurs in the kissing number problem of finding the maximum number of unit spheres in Euclidean space that can be tangent to a central unit sphere without any two spheres intersecting beyond a point of tangency. The center points of these spheres have a minimum spanning tree in the form of a star, with the central point adjacent to all other points. Conversely, for any vertex V of any minimum spanning tree, one can construct non-overlapping unit spheres centered at V and at points 2 units along each of its edges, with a tangency for each neighbor of V. Therefore, in n-dimensional space, the maximum possible degree of a vertex, the number of spanning tree edges connected to it, equals the kissing number of spheres in n dimensions. Planar minimum spanning trees have degree at most 6, and when a tree has degree 6, there is always another minimum spanning tree with maximum degree 5. Three-dimensional minimum spanning trees have degree at most 12. The only high dimensions in which the exact value of the kissing number is known are 4, 8, and 24 dimensions. For points generated at random from a given continuous distribution, the minimum spanning tree is almost surely unique. The numbers of vertices of any given degree converge for a large number of vertices to a constant times the number of vertices. The values of these constants depend on the degree and the distribution. However, even for simple cases such as the number of leaves for points uniformly distributed in a unit square, the precise values are not known. Empty regions. Upright equals 1.2 thumb empty regions for the Euclidean minimum spanning tree. For the red edge shown, these regions cannot contain any of the vertices of the tree. White, the empty lens defining the relative neighbourhood graph. Light blue, the diameter circle defining the Gabriel graph and forming an empty circle for the Delaunay triangulation. Dark blue, a 60 degrees, 120 degrees rhombus that cannot overlap with the rhombi of other spanning tree edges. For any edge UV of any Euclidean minimum spanning tree, the lens or vescopuscus formed by intersecting the two circles with UV as the radii cannot have any other given vertex W in its interior. Put another way, if any tree has an edge UV whose lens contains a third point W, then it is not of minimum length. For, by the geometry of the two circles, W would be closer to both U and V than they are to each other. If edge UV were removed from the tree, W would remain connected to one of U and V, but not the other. Replacing the removed edge UV by U or VW, whichever of these two edges reconnects W to the vertex from which it was disconnected, would produce a shorter tree. For any edge UV over any Euclidean minimum spanning tree, the rhombus with angles of 60 degrees and 120 degrees, having UV as its long diagonal, is disjoint from the rhombi formed analogously by all other edges. Two edges sharing an endpoint cannot have overlapping rhombi because that would imply an edge angle sharper than 60 degrees, and two disjoint edges cannot have overlapping rhombi. If they did, the longer of the two edges could be replaced by a shorter edge among the same four vertices. Supergraphs. Certain geometric graphs have definitions involving empty regions and point sets from which it follows that they contain every edge that can be part of a Euclidean minimum spanning tree. These include the relative neighbourhood graph, which has an edge between any pair of points whenever the lens they define is empty. The Gabriel graph, which has an edge between any pair of points whenever the circle having the pair as a diameter is empty. The Delaunay triangulation, which has an edge between any pair of points whenever there exists an empty circle having the pair as a chord. The Euclidean graph formed from the Delaunay triangulation by removing the longest edge of each triangle. For each remaining edge, the vertices of the Delaunay triangles that use that edge cannot lie within the empty lune of the relative neighbourhood graph. Because the empty region criteria for these graphs are progressively weaker, these graphs form an ordered sequence of subgraphs. That is, using to denote the subset relationship among their edges, these graphs have the relations in the graph guaranteed to contain the minimum spanning tree as the Yale graph determined for points in the plane by dividing the plane around each point into 60 degrees wedges and connecting each point to the nearest neighbour in each wedge. The resulting graph contains the relative neighbourhood graph because two vertices with an empty lens must be the nearest neighbours to each other in their wedges. As with many of the other geometric graphs above, this definition can be generalized to higher dimensions, and unlike the Delaunay triangulation, its generalizations always include a linear number of edges. Total length. For endpoints in a unit square or any other fixed shape, the total length of the minimum spanning tree edges is $or\sqrt n$. Some sets of points, such as points evenly spaced in $\sqrt n\times\sqrt n$ great attain this bound. For points in a unit hypercube in d-dimensional space, the corresponding bound is on d-1/d. The same bound applies to the expected total length of the minimum spanning tree for endpoints chosen uniformly and independently from a unit square or unit hypercube. Returning to the unit square, the sum of squared edge lengths of the minimum spanning tree is un. This bound follows from the observation that the edges have disjoint rhombi with area proportional to the edge length squared. The $o\sqrt n$ bound on total length follows by application of the Cauchy-Schwarz inequality. Another interpretation of these results is that the average edge length for any set of points in a unit square is $un/sqrt n$ at most proportional to the spacing of points in a regular grid, and that for random points in a unit square the average length is proportional to $1/sqrt n$. However, in the random case with high probability, the longest edge has length approximately $\sqrt\frac\log n/pi longer than the average by a non-constant factor. With high probability, the longest edge forms a leaf of the spanning tree and connects a point far from all the other points to its nearest neighbour. For large numbers of points, the distribution of the longest edge length around its expected value converges to a Laplace distribution. Any geometric spanner, a subgraph of a complete geometric graph whose shortest paths approximate the Euclidean distance, must have total edge length at least as large as the minimum spanning tree, and one of the standard quality measures for a geometric spanner is the ratio between its total length and of the minimum spanning tree for the same points. Several methods for constructing spanners, such as the greedy geometric spanner, achieve a constant bound for this ratio. It has been conjectured that the Steiner ratio, the largest possible ratio between the total length of a minimum spanning tree and Steiner tree for the same set of points in the plane, is $2/\sqrt3\approx 1.1547, the ratio for 3 points in an equilateral triangle. Subdivision. If every edge of a Euclidean minimum spanning tree is subdivided by adding a new point at its midpoint, then the resulting tree is still a minimum spanning tree of the augmented point set. Repeating this subdivision process allows a Euclidean minimum spanning tree to be subdivided arbitrarily finely. However, subdividing only some of the edges, or subdividing the edges at points other than the midpoint, may produce a point set for which the subdivided tree is not the minimum spanning tree. Computational complexity. For points in any dimension, the minimum spanning tree can be constructed in time onto by constructing a complete graph with an edge between every pair of points weighted by Euclidean distance, and then applying a graph minimum spanning tree algorithm such as the Prim-Dijkstra-Jonic algorithm or Burke's algorithm on it. These algorithms can be made to take time onto on complete graphs, unlike another common choice, Kruskal's algorithm, which is slow because it involves sorting all distances. For points in low-dimensional spaces, the problem may be solved more quickly as detailed below. Computing Euclidean distances involves the square root calculation. In any comparison of edge weights, comparing the squares of the Euclidean distances instead of the distances themselves yields the same ordering, and so does not change the rest of the tree's computation. This shortcut speeds up calculation and allows a minimum spanning tree for points with integer coordinates to be constructed using only integer arithmetic. 2 dimensions. A faster approach to finding the minimum spanning tree of planar points uses the property that it is a subgraph of the Delaunay triangulation. 1. Compute the Delaunay triangulation, which can be done in nlog n time. Because the Delaunay triangulation is a planar graph, it has at most 3 minus 6 edges. 2. Label each edge with its squared length. 3. Run a graph minimum spanning tree algorithm. Since there are on edges, this requires nlog n time using any of the standard minimum spanning tree algorithms. The result is an algorithm taking nlog n time, optimal in certain models of computation see below. If the input coordinates are integers and can be used as array indices, faster algorithms are possible. The Delaunay triangulation can be constructed by a randomized algorithm in nlog log n expected time. Additionally, since the Delaunay triangulation is a planar graph, its minimum spanning tree can be found in linear time by a variant of Borofka's algorithm that removes all but the cheapest edge between each pair of components after each stage of the algorithm. Therefore, the total expected time for this algorithm is nlog log n. In the other direction, the Delaunay triangulation can be constructed from the minimum spanning tree in linear time bound nlog asterisk n, where log asterisk denotes the iterated logarithm. Higher dimensions. The problem can also be generalized to endpoints in the d-dimensional space $\odd $d. In higher dimensions, the connectivity determined by the Delaunay triangulation, which likewise partitions the convex hull into d-dimensional simplices, contains the minimum spanning tree. However, the triangulation might contain the complete graph. Therefore, finding the Euclidean minimum spanning tree as a spanning tree of the complete graph or as a spanning tree of the Delaunay triangulation both take odd and 2 time. For 3 dimensions, the minimum spanning tree can be found in time nlog n 4/3, and in any greater dimension in time $left and 2 \frac 2 \lcld/2. Seal plus 1 plus for epsilon. $8 for any epsilon 0 faster than the quadratic time bound for the complete graph and Delaunay triangulation algorithms. The optimal time complexity for higher dimensional minimum spanning trees remains unknown, but is closely related to the complexity of computing bichromatic closest pairs. In the bichromatic closest pair problem, the input is a set of points given 2 different colors, say, red and blue. The output is a pair of a red point and a blue point with the minimum possible distance. This pair always forms one of the edges in the minimum spanning tree. Therefore, the bichromatic closest pair problem can be solved in the amount of time that it takes to construct a minimum spanning tree and scan its edges for the shortest red-blue edge. Conversely, for any red-blue coloring of any subset of a given set of points, the bichromatic closest pair produces one edge of the minimum spanning tree of the subset. By carefully choosing a sequence of colorings of subsets and finding the bichromatic closest pair of each subproblem, the minimum spanning tree may be found in time proportional to the optimal time for finding bichromatic closest pairs for the same number of points, whatever that optimal time turns out to be. For uniformly random point sets in any bounded dimension, the subgraph or Delaunay triangulation of linear expected numbers of edges are guaranteed to contain the minimum spanning tree and can be constructed in linear expected time. From these graphs, the minimum spanning tree itself may be constructed in linear time by using a randomized linear time algorithm for graph minimum spanning trees. However, the poor performance of these methods on inputs coming from clustered data has led algorithm engineering researchers to develop methods with a somewhat slower nlog n time bound for random inputs or inputs whose distances in clustering resemble those of random data, while exhibiting better performance on real-world data. A well-separated pair decomposition is a family of pairs of subsets of the given points, so that every pair of points belong to one of these pairs of subsets, and so that all pairs of points coming from the same pair of subsets have approximately the same length. It is possible to find a well-separated pair decomposition with a linear number of subsets and a representative pair of points for each subset, in time nlog n. The minimum spanning tree of the graph formed by these representative pairs is then an approximation to the minimum spanning tree. Using these ideas, a 1 plus epsilon approximation to the minimum spanning tree may be found in nlog n time for a constant epsilon. More precisely, by choosing each representative pair to approximate the closest pair in its equivalence class and carefully varying the quality of this approximation for different pairs, the dependence on epsilon in a time bound can be given as $on\log n plus \v epsilon minus 2 \log 2 /t frac 1 \v epsilon n $ for any fixed dimension. Dynamic and kinetic. The Euclidean minimum spanning tree has been generalized in many different ways to systems of moving or changing points. If a set of points undergoes a sequence of dynamic insertions or deletions of points, each of these updates induces a bounded amount of change to the minimum spanning tree of the points. When the update sequence is known in advance for points in the plane, the change after each insertion or deletion can be found in time nlog 2m per insertion or deletion. When the updates must be handled in an online manner, a slow but still polylogarithmic nlog n time bound is known. For high-dimensional versions of the problem, the time per update is slower, but still sublinear. For endpoints moving linearly with constant speed, or with more general algebraic motions, the minimum spanning tree will change by a sequence of swaps in which one edge is removed and another replaces it at a point in time where both have equal length. For linear motions, the number of changes is at most slightly larger than n25/9. For more general algebraic motions, there is a near cubic upper bound on the number of swaps based on the theory of Davenport-Skinner sequences. The minimum moving spanning tree problem again concerns points moving linearly with constant speed over an interval of time and seeks a single tree that minimizes the maximum sum of weights occurring at any instant during this interval. It is NP hard to compute exactly, but can be approximated to within a factor of 2 in polynomial time. The kinetic Euclidean minimum spanning tree problem asks for a kinetic data structure that can maintain the minimum spanning tree as its points undergo both continuous motions and insertions and deletions. Several papers have studied such structures, and a kinetic structure for algebraically moving points within their cubic total time, nearly matching the bound and the number of swaps, is known. Lower bound. An asymptotic lower bound of omega log n of the Euclidean minimum spanning tree problem can be established in restricted models of computation. These include the algebraic decision tree and algebraic computation tree models, in which the algorithm has access to the input points only through certain restricted primitives that perform simple algebraic computations on their coordinates. In these models, the closest pair of points problem requires omega log n time, but the closest pair is necessarily an edge of the minimum spanning tree, so the minimum spanning tree also requires this mesh time. Therefore, algorithms for constructing the planar minimum spanning tree in time nlog n within this model, for instance by using the Delaunay triangulation, are optimal. However, these lower bounds do not apply to models of computation with integer point coordinates, in which bitwise operations and table indexing operations on those coordinates are permitted. In these models, faster algorithms are possible, as described above. Applications. An obvious application of Euclidean minimum spanning trees is to find the cheapest network of wires or pipes to connect a set of places, assuming the links cost a fixed amount by unit length. The first publications on minimum spanning trees more generally concerned a geographic version of the problem involving the design of an electrical grid for southern Moravia, and an application to minimizing wire lengths in circuits was described in 1957 by Loberman and Weinbutcher. Minimum spanning trees are closely related to single linkage clustering, one of several methods for hierarchical clustering. The edges of a minimum spanning tree, sorted by their length, give the order in which to merge clusters into larger clusters in this clustering method. Once these edges have been found by any algorithm, they may be used to construct the single linkage clustering in time nlog n. Although the long thin cluster shapes produced by single linkage clustering can be a bad fit for certain types of data, such as mixtures of Gaussian distributions, it can be a good choice in applications where the clusters themselves are expected to have long thin shapes, such as in modelling the dark matter halos of galaxies. In geographic information science, several researcher groups have used minimum spanning trees of the centroids of buildings to identify meaningful clusters of buildings, for instance, by removing edges identified in some other way as inconsistent. Minimum spanning trees have also been used to infer the shape of curves in the plane, given points sampled along the curve. For a smooth curve, sampled more finely than its local feature size, the minimum spanning tree will form a path connecting consecutive points along the curve. More generally, similar methods can recognize curves drawn in a dotted or dashed style rather than as a single connected set. Applications of this curve-finding technique include particle physics in automatically identifying the tracks left by particles in a bubbled chamber. More sophisticated versions of this idea can find curves from a cloud of noisy sample points that roughly follows the curve outline by using the topology of the spanning tree to guide a moving least squares method. Another application of minimum spanning trees is the constant factor approximation algorithm for the Euclidean travelling salesman problem, the problem of finding the shortest polygonalization of a point set. Walking around the boundary of the minimum spanning tree can approximate the optimal travelling salesman tour within a factor of 2 of the optimal length. However, more accurate polynomial time approximation schemes are known for this problem. In wireless ad hoc networks, broadcasting messages along paths in a minimum spanning tree can be an accurate approximation to the minimum energy broadcast routing, which is again hard to compute exactly. Realization. The realization problem for Euclidean minimum spanning trees takes an abstract tree as input and seeks a geometric location for each vertex of the tree in a space of some fixed dimension such that the given tree equals the minimum spanning tree of those points. Not every abstract tree is such a realization. For instance, a tree must obey the kissing number bound on the degree of each vertex. Additional restrictions exist. For instance, it is not possible for a plane in minimum spanning tree to have a degree 6 vertex adjacent to a vertex of degree 5 or 6. Determining whether a two-dimensional realization exists is NP hard. However, the proof of hardness depends on the fact that degree 6 vertices in that tree have a very restricted set of realizations. The neighbours of such a vertex must be placed on the vertices of a regular hexagon centered at the vertex. Indeed, for trees of maximum degree 5, a planar realization always exists. Similarly, for trees of maximum degree 10, a three-dimensional realization always exists. For these realizations, some trees may require edges of exponential length and bounding boxes of exponential area relative to the length of their shortest edge. Trees of maximum degree 4 have smaller planar realizations with polynomially bounded edge lengths and bounding boxes.